Professor, you're muted.
Sorry about that. Thank you for letting me know. All right, so as I was saying, the lines that you see here are conductors. And those conductors basically conduct electricity and voltage from one point in the circuit to another. Now, in real life, conductors have some resistance, they will have some inductance, and they will have some capacitance. But in circuit analysis, on paper, when we do theoretical circuit analysis, the conductors are ideal, meaning they have zero resistance, they have zero inductance, and they have zero capacitance. Okay. Conductor, if I was to take a wire from one end of this wall to the other end of the wall, it will lose some value. If I'm going to transmit some current from one end to the other, it will lose some value. But ideal conductors are lossless. So ideal conductors, 0 ohm resistance, and they are lossless. No loss will occur. So anytime you perform an experiment in the lab, that conductor will have some resistance, might be very, very small, even small that you cannot even measure it. So let's say 0.1 ohm or 0.2 ohms. So if you perform a calculation in the lab, you may want to account for that. But any calculations that you do for the theory, you use it as 0. Make sense? All right. So theoretical analysis is all based on ideal value of components. If resistance is 10 ohms, we use 10. We do not use 10.1 or 9.9. Practically, when you perform an experiment, you would actually measure. If it comes out to be 10.1 or 10.2, you would use that value to perform the calculations. So that is the big difference between theoretical calculations and anything that you perform experimentally in real life. And capacitors, again, we'll talk more about those when we get to chapters 3 and 4. Capacitors are two parallel plates. There are multiple symbols in existence. Some of the symbols simply have two parallel lines. Sometimes they have symbols shown like this. You have one flat line and one curved line. And inductors are coils. They are coils, and hence the symbol for an inductor is a spiral. Okay. This is a source. A circular symbol is used for a source or for a measurement device. Okay, so source and measurement device is usually a circle. Now, if you have a plus minus sign inside, this plus minus notifies that it's voltage. If you have an arrow, it is current. If you have an arrow at an angle, it notifies it is a measurement device. It basically comes from the needle that is in analog meters. And so an arrow that is at an angle notes that this is a measurement device. So here in this circuit, we see that there's a circle with a plus and minus inside it. Hence, it is a voltage source. If there was an arrow inside it, whether it's pointing straight up or pointing horizontal or vertical, it's a current source. All right, any questions? Measurement and measurement. Sorry, that's the and. That's the and. So source and measurement devices both use a circular symbols. So here, just examples of what we just talked about. This is voltage source. This is a current source. Now here in the circuit, you have drawn it vertically. It could be horizontal also. So voltage source could be like this, and a current source also could be like this. The direction does not matter. The plus and minus could be switched. The arrow also could be switched. But again, this is voltage source. This is current source. Anyone know what the diamond symbol is? The diamond notes a dependent source. So the circle, the circular sources are for independent sources. The diamond is for a dependent source. Okay. So this is independent. And this is a dependent source. Now, you need to understand this is purely theoretical. Okay. Use these for analysis and calculation purposes. In real life, well, theoretical or real life, a dependent source is used to signify a quantity that is dependent on some other part of the circuit. Okay, so a dependent source here, this is a dependent voltage source and this is a dependent current source. So a dependent voltage source supplies a voltage value, but it depends on some other part of the circuit to supply that quantity. Similarly, for the current source, a current source that is dependent signifies that it is supplying that current at that point in the circuit, but it depends on some other part of the circuit in order to supply that value. And it is used mostly for theoretical analysis purposes. So we are required to teach both independent as well as dependent sources. So I will have one or two problems perhaps based on dependent sources, but for the most part, everything that we do in 201 has to do with independent sources. Okay. Voltage and current. Now, here we see a voltage source and here we see a current source on the right. Okay. But in real life, you cannot have one without the other. If you have voltage, you have current. If you have current, you have voltage. Okay, they cannot exist without each other. The difference is that when you say a voltage source, meaning it supplies a fixed value of the voltage. Actually, source supplies a fixed value, while the other value can be changed. So a 5-volt voltage source will supply 5 volts irrespective of the current requirement. Okay. Same thing for the current. A fixed value of current will be supplied by a current source while the voltage could change. And we'll talk more about this once we get with once we come to Ohm's law. If you are taking 251, the lab, you will see that the voltage and current sources is one piece of equipment. You simply change the mode from constant voltage to constant current. When it's constant voltage, it's working as a voltage source. When you switch it to constant current mode, CC mode, it's now working as a current source. Okay, but again, make no mistake. Whether you run it as voltage source, whether you run it as current source, both quantities are being supplied. Okay, voltage source will keep a fixed voltage, but will change the current depending on what the load requires. And a constant current source will provide a constant current, but will change the voltage depending on what the load requires. Okay. Oh, one other thing in the previous slide. This is a source. Okay, it's supplying energy. Anything that supplies energy is a source. Anything that consumes energy is a load. And so all of these right here, R, L, and C, is a load. So again, anything that supplies energy is a source. Anything that consumes energy or receives energy is a load. So our job in this, yes. So measurement devices are designed such that they do not consume any energy. So theoretically, so the question being asked is whether a measurement device is considered to be a load. Well, it does not supply energy. So the answer is no, it's not a source. And in real life too, the devices are designed in such a way that they would consume as little energy as possible. They might consume a little bit, but they would not change the measurement as much. So you could say theoretically that it would be a load. All right, so question I had here was, what is circuit analysis? Well, circuit analysis is basically trying to determine the values of the physical quantities in the circuit, any portion of the circuit. So once the source supplies some energy, our job is to figure out what the voltage, the current, the power, the energy could be at any of the points in the circuit. So whether it's for the resistor, capacitor, inductor, or any other part of the circuit, we need to figure out the value of that physical quantity. Yes. Oh, so question being asked is, what is RLC? That's a good question, because sometimes I tend to forget that students may have done the prereq. It's been a long time, so I need to go through the symbols also. So R is for the resistor, L is for inductor, and C is for capacitor. Resistor, inductor, capacitor. Chapters 1 and 2 deal with resistive circuit analysis. Chapters 3 and 4 deal with capacitors and inductors. And then chapters 5, 6, and then 7 or 5.5 in this book deals with AC analysis applied to all three components. All right, 10-second pause. Let me know if you have any questions. Okay. I don't have anything particular about this slide. I just like the meme, so I wanted to put it in there. Basically, it's like, when you first start out and students are not familiar with it, especially like high school students who may not inquire this, I would just like to say Thor is here to help you understand. But in this class, as I was showing, we deal with three components: resistor, inductor, and capacitor. We'll also look at transformers a little bit. Transformers are nothing but two interwinding coils of inductances, right? Transistor or transistor is something that you would learn in electronics, which is EE321. So if you're required to take EE321, that's where you would learn about solid state devices. Minor plug, I am teaching 2 sections of 321 next quarter. If you are required to take that class, or if you're thinking about taking that class as an elective, I will use the exact same system that I'm using for this class. And the code that you purchase for this class will also work for 321 without needing to purchase it again. So just as an FYI. All right, unit prefixes. As engineers, we deal with a large variation in the numbers that we deal with. Doesn't matter what field of engineering you are in, whether you're mechanical, industrial, civil, we deal with large numbers, and sometimes we also deal with very, very small numbers. And so we have the unit prefix system that allows us to easily note the large quantities as well as the small quantities. Most of the time, we work in the middle of this table right here. And I don't expect students to memorize everything, but there are some terms or some unit prefixes that have become part of like pop culture. And so even if you are not an engineer, you would be familiar with most of those, right? So I just want to point out like two examples, one for very small unit prefixes and one for very large ones. Micro and nanotechnology, the words keep getting thrown around a lot. Microchip, microchip, microchip. Well, micro, again, is a prefix that says it's e raised to minus 6, 10 raised to minus 6, right? 10 raised to minus 6 meters. So if you take 1 millimeter, which, assume everybody knows how small a millimeter is. 1 millimeter is 10 raised to minus 3 meters. You take that 1 millimeter and you divide it into 1,000 parts. That is 1 micron. That is 1 micrometer. 1 micrometer is noted by the word micron. So 1 micron is 10 raised to minus 6 meters. Just to give you an idea of how small that micron is, a human hair, which I don't have much left, is on the order or in the size of about 70 microns. So human hair, 70 microns, really, really thick. And that's the reason I was saying, when you go into a clean room semiconductor facility, you might have seen videos or pictures where they're gowned up from head to toe in a white bunny suit. That's what we call them, bunny suits. Okay, that bunny suit is not to protect the user. It's to protect the environment from the user. So humans, we shed a lot. We shed skin cells, we shed hair, we shed dust particles. And each of those dust particles can contaminate the work that we're trying to do, right? And so we wear everything from we cover everything up from head to toe before we go into that cleanroom facility. And the reason is because even if one single hair piece falls out and goes into the equipment, it's going to render everything useless. Nano is, of course, if you take 1 micron and divide it into a further 1,000 parts. So there's absolutely no way we can see anything on the order of a micron or 1 nanometers. Okay, it's that small. On the other end of the scale, we have mega, giga, and tera. You'll be familiar with those when we talk about storage, RAM memory, hard drive storage, frequencies. We work in the megahertz, in the gigahertz range. The most common example that everyone uses is 2.4 gigahertz. Giga is 10 raised to 9, basically just tells you that the value of that signal is changing 10 raised to 9 times per second. That fast. Okay. So mega is a million, right? Mega is a million, and giga would be a billion. So to illustrate the difference between a millionaire and a billionaire, let's use the concept of time. How much do you think is 1 million seconds in terms of days, weeks, months? Just a wild guess. 2 weeks, 4 months, 4 years. So 1 million seconds is less than 12 days. So about 2 weeks was the closest. So it's about 11.7 or something days. How much do you think is 1 billion seconds? 32 years, absolutely correct. Is 31 point some years. That's the difference between a millionaire and a billionaire. Okay, you can only dream. Days versus years. Anyone seen the movie In Time? No one? It's one of my favorite movies. Check it out. Justin Timberlake. The concept is very intriguing. It's basically about a society where everybody lives until 25 years of age, and they have a clock on their hand. After 25, you need to buy time. If you don't buy time, you are done. Basically, the person, you're dead. And so it shows how poor people live day to day, just trying to, earn enough time. Like they do work, they get paid in time. So they try to work as hard as possible, but there's never enough time. And the rich, they have like, billions and millions of years. In Time, that's the movie. Anyway, any questions about unit prefixes? Again, as I said, I don't expect you to memorize this, but as engineers in your own field, you would be using these. So you should be familiar with most of them. All right. Conductor, electrical circuits, and the fluid flow analogy. Okay. If you have, let's say, a pipe, the pipe is carrying some sort of fluid, let's say water. Okay. We can use that analogy to make a equivalence between mechanical system and an electrical system. So the pipe would be analogous to a conductor. The fluid flowing through the pipe would be similar to electrical current. And voltage would be the pump or the pressure that's allowing or forcing the fluid to flow through. The pressure differential. Okay, the pressure differential at two ends would allow or would force that current to flow through. Now, a mechanical valve and an electrical switch, they are the exact opposite. Now I'll show you how. If you have a valve, let's say you have some sort of pipe in there. Now valves can be, of course, open or closed, but in simple terms, let's say there's this valve in the pipe. When it's closed, as you see here in the illustration, when a valve is closed, let's see. Valve and electrical switch. When a valve is closed, it will block the flow of fluid, right? An electrical switch is the exact opposite. Electrical switch is noted by something like this. Okay, and again, we'll see these a lot in chapter 4. So electrical switch, if it's closed, it will permit the flow. There cannot be a break in an electrical circuit. If there's a break in an electrical circuit, that means that voltage or current does not flow. There's no pathway for the current to flow. Important point, electrical current always needs a closed path to flow. If it's open, it does not flow. The most common example is your power outlet. Power outlet has 2 points, right? It's an open loop until you plug something in that in that power outlet, that loop is not closed. You could, of course, insert a wire in the two prongs, and what would happen? Don't do that. It's a short circuit, right? It should still work, but what happens is if you take a piece of wire and stick it into the 2 points of a power outlet, that current is now flowing from point one. It's a closed loop, so current now flows through. But because it's high voltage and high current, that wire, which is a very, very low resistance, cannot handle that high amount of current. And so you see a spark and it blows out. That's what an actual fuse is. If the current exceeds the fuse capacity, it blows out and it interrupts the circuit. That's what it is. If you take a wire with a very high resistance and you stick it into the power outlet, nothing will happen. The wire would just get hot, but there would not be any spark. As long as that conductor can handle the current and the voltage coming through, it'll be fine. Anyway, coming back to the main point, electrical current always needs a closed path to flow through. So an electrical switch needs to be closed in order for current flow to go through. Mechanical valve, when open, will permit the flow. An electrical switch, when open, will block the flow. So the mechanical to electrical analogy is good, but there are differences in a mechanical valve and an electrical switch. So anytime you hear the words, the switch is open, if the switch is open, that means there is a break in the line. Electrical switch open, current cannot flow through. Electrical switch closed, current can pass. All right, think over it. Let me know if you have any questions. All right, moving on. When we first begin circuit analysis, we have no idea. We have no idea what quantity is appearing where. We have no idea of the values, right? So what we do is we simply assign values randomly, or at least we assign variables randomly. And it's completely arbitrary. Okay, we have no idea if the current is going up, it's going down, if the voltage has a plus or minus sign at a different point. We have absolutely no idea, right? I say current is flowing through, right? Current is flowing through, meaning it has direction. It's flowing from one point to another point. If we plot and have an illustration like this, we could say current is actually flowing up or flowing down. But an actual electrical circuit, it does not know, it does not care. We just know it's entering through one point and exiting out of the other point. So in this case, in this illustration right here, we say we have element A. We have no idea what that element is right now, but we simply assign the current I1 flowing through A as going up. Or more appropriately, I would say it is entering from this point and exiting out of this end. Okay, so the current is flowing here, coming out here. Same thing with I2 and I3. Current, when I would have again assumed that students would be familiar, but current in electrical engineering is noted by I. Current is noted with the letter I, and the unit is named after ampere, or simply amps, or amp. And voltage is noted by V. Could be uppercase or lowercase. And named after volta, so it's volt, or simply V. A, V. So sometimes it can get confusing, okay? The symbol for current is I, capacitor is a C, unit for current is ampere or amp for short, noted by the letter A. Voltage is V, and the unit is also V. Power is noted with P, and the unit is unit for power. James Watt. What? W. Sometimes also gets confusing because then we have energy also has the same letter, but we'll cross that bridge later. So voltage is nothing but the difference in potential between 2 points. Okay, voltage is nothing but the difference in potential. So it's an electrical potential difference between 2 points. If we had 2 points, oh, I have voltage polarity. If you had 2 points in a circuit, if they're the exact same potential, then the difference between those 2 points is 0. So the voltage between those 2 points would be 0. Okay, so let me use this illustration right here. Let's say, electrically speaking, this is the 0 volt line. Okay, 0 volts with reference to ground. Now, if you have point A right here, and I don't know, maybe it's at +5 with respect to ground. So level of point A is +5 volts. Then you have B, which is also at +5 volts. Difference in potential between A and B is 0. So the voltage between A and B is 0. Make sense? Voltage is the difference in electrical potential between any 2 points. Simply stated, is the potential difference. Okay, long form is the difference in electrical potential between any 2 points. So it doesn't matter what the value of the voltage is with reference to ground, which is 0 volts, as long as they have the same exact voltage potential, then the difference is 0 volts, then the voltage between those 2 points is 0. Point C, let's say, is at 2 volts. So we would say voltage at C with reference to 0 volts is 2 volts, but the voltage between A and C is 3. Same thing with B and C. How about if you have D at, let's say, -2 volts? Minus simply signifies that it's below a certain level. Electrical circuits do not know or do not care. It's just for us humans to be able to make sense of all the values. Hence, we use a plus and a minus. Okay. It also has to do with how we use the reference. And again, we'll get to that in like about 2 slides. What is the difference between C and D? 4 volts. So if I was measuring the voltage between C and D, it would be 4 volts. If I was measuring the voltage between A and D or B and D, it would be 5 plus 2, which is 7 volts. Let's take a 10-second pause and think over it. Let me know if you have any questions. Yes. In what sense? Yeah. It can be. Depends on how we look at it. Yes. Polarity. So we'll get to that in about 2 slides. Any other questions? Okay. See, we have about 7-8 minutes left. Oh, assigning values randomly, same thing with voltage. Okay. We assign, again, as I said, voltage is the difference in potential between 2 points. If there's no difference, it's 0. If there is a difference, we take the lower value and we assign minus to it, and the other value is a plus to it. And we call that the polarity of the voltage. Okay, polarity of the voltage. So reference direction for current, and reference polarity for voltages. Here we have an element which has 2 points, A and B. If you have the current, or if we assume the current that is flowing from A to B, we note it as IAB. IAB. The first subscript is the point of origin or the point of entry. And the second subscript is the point of exit, meaning the current is flowing from point A to point B. Okay, point A to point B. Again, remember, a couple of slides ago, I said we assign values randomly. At the beginning of our analysis, we have no idea whether the current is flowing in this direction or up or down or left or right. We simply assign current direction randomly. At the end of our calculations, if it turns out that this value IAB was negative, let's say if IAB turns out to have a negative value, by the way, I use a minus sign with a VE to note negative. Okay, just to let you know. If IAB turns out to have a negative value, what do you think it means? It's just going up instead of going down, or instead of going in the direction that we assumed at the beginning, it is simply going in the opposite direction. It does not mean that your answer is incorrect. Very important to note. If you note at the beginning of your problem or the beginning of your solution, if you note a single direction for the current, if the answer turns out to be negative, all you're doing, or all it is showing, is that it is going in the opposite direction. That's all. So in this case, we have IAB, current going from A to B, and IBA going from B to A. So mathematically, I could write IAB is equal to minus IBA, and vice versa. Could also write IBA is equal to minus IAB. All right. Any questions? Same thing for the voltage. Voltage has a polarity. We have a plus sign and a minus sign. We use double subscripts on the variables. VAB simply means I'm measuring my voltage at point A with my reference at point B. Okay. When you measure the voltage, see, current flows through an element. Current flows through an element, so we are talking about direction. But voltage is measured across. Okay. Current is always through an element, so current is always through, and voltage is always across. So it's measured across 2 points. So if I was to take and measure the voltage at point A, if I'm measuring at point A, what am I comparing it to? Again, remember, voltage is the potential difference, right? So where am I measuring the voltage with respect to? So in this case, I'm measuring with reference to B. And so it's VAB. You're measuring voltage at A with my reference at B. I'm standing at B and I'm looking at A. Does that make sense? Now, A could be above me, A could be below me. If it's above me, it's positive. It's below me, it's negative. But at the beginning of the problem, at the beginning of your solution, you don't really know and you don't really care. You simply assume a value and you assign a polarity to the voltage and you begin your calculations. VBA simply means you're measuring voltage at B, which is the first subscript, with reference to A. So in this case, you are now standing at A and you're looking at B. And similar to the current, VAB is equal to minus VBA, or VBA is equal to minus VAB. Mathematically, we use plus and minus signs so that the equation makes sense. In real life, again, the actual components do not know and do not care, right? We use plus and minus signs so that it makes sense to us and so that the equations balance out. Again, it all goes back to the law of conservation of energy, right? If a source is supplying some amount of energy and the load is consuming, and we'll get to that also in a little bit. And so we use plus and minus signs to balance out that equation. Otherwise, it wouldn't work at all. So again, any questions about the two subscript notation, A and B to A? Voltage, VAB means measurement at A with reference to B. VBA means measurement at B with reference to A. All right. One final thing for today is Ohm's law. Again, I like the meme. There are plenty of memes about Ohm's law. I just like this one. And I assume students are familiar with Ohm's law from physics, a little bit, right? George Ohm was a physicist who came up with this equation, V equals IR. You could solve every electrical circuit problem with this equation. Well, when I say solve it, I mean you cannot solve it without using this equation. V equals IR. Voltage is the product of the current that is flowing through the resistance. V equals I times R. V is the voltage, I is the current, R is the resistance. So in terms of units, volts equal amps times ohms. Oh, resistance units. We talked about how voltage unit is named after volta, current unit is named after ampere, resistance named after George Ohm. It's also noted by the Greek letter omega. Omega. We have the opposite of resistance, which is the conductance. Again, we'll talk about that later. But for now, again, Ohm's law, the most important law in electrical engineering. You cannot solve any circuit without it. V equals IR. From here, we also get I is V over R and R is V over I. All right, that's it. Thank you very much for coming to class today. We'll pick up here again on Friday.